Thanks for being here. I was waiting for MIT time, so I think we're more or less okay to get started. This is a very first seminar for the semester, so it's great to see a good turnout. Thank you all so much. It helps that we have a celebrity speaker, Professor Sendhil Mullainathan. He doesn't need much of an introduction, but I will say a few kind of general. I'll make a few general points about his great trajectory. He's the Roman Family University Professor of Computational Behavioral Science at Chicago Booth, but teaching 2 courses here this semester. I don't know if some of you will be taking them. His past work has combined insights from economics and behavioral science with causal inference tools, and I'm sure several of you have seen a lot of these papers on discrimination and poverty. He's a member of the American Academy of Arts and Sciences, a MacArthur Genius Grant recipient, a former professor at Harvard, and I think he also started here at MIT, and we're hoping to get him back. So please, intelligent questions only, please. And he'll be presenting on integrating behavioral economics and machine learning. Thanks so much for being here.
Thanks so much. I'm just going to dive right in. I feel free to just dive in with questions anytime you want. So let me just give you sort of 3 principles that guide my work. I want to give kind of an overview talk about what I'm thinking about at a very high level right now. So I think the first principle is even I know how to use a Venn diagram. So the first principle is there's a lot of important work to be done at this intersection. So that's like ML plus behavioral, I think, is a fertile area. And I think it's fertile because if you look at the literature on AI in society, whether it's fairness or whatever, I actually think if you dig into many of these papers, you'll often find that many of the algorithms that fail often involve misunderstandings about people because they are generated on data by people. But I also think many of the most interesting opportunities come from a better understanding of people. And that is what psychologists have done. And behavioral economists have co-opted an entire field by calling it behavioral economics. It's really kind of psychology. The converse is that existing tools that we have over here, standard supervised learning pipelines, reinforcement learning, et cetera, they're not sufficient for integrating the formal models we have of people. I think the raw ingredients are there, but I think we'll need to build new tools for integrating these two. So that's the sense in which I think it's a fertile area. There's new tools needed for doing stuff at the intersection. The third principle behind my work involves this. Does anyone know what this is? I'd be just shocked if anybody knew what this was, but I'll throw it out there. Somebody may. No. David, you're my best shot on goal. No. It's, I won't even try and say it. It's a Rodamset experimental station. You might be like, why on earth would I know what that is? This is around the turn of the 20th century. It was a place where they spent a lot of resources trying to increase British farm productivity, which I know must be close to all of your hearts. In fact, there's a direct link between what was done there, and not just direct, but that's where ANOVA comes from, block randomization, Latin square designs come from. That's where the idea of confounding comes from. That's where Fisher's exact test comes from. It's because during this period, we were starting to do experimental work, and in that, trying to make sense of the concrete problems of like, which farm is more productive, which input is more productive, all of these foundational statistical tools arose. I say this as a reminder that very often when we're building tools, it is very easy to get infatuated and start from the other direction. But the most interesting things of statistics have always come from looking at real problems. So here, the third principle that guides my work is that intense focus on applications, I think, surfaces theoretically important questions and methodological questions. And when I say intense focus, I mean actually taking the problem itself incredibly seriously. Because you actually care about, not as an application of some tool you already have in mind. So that's what I'm going to do today. I'm going to try and focus on 3 applications. And I'd say that it always goes like this. There's an applied problem. There's a hack. That's probably a bit ungenerous way of saying, so let's call it specific solution. That's the dressed up way of saying hack. There's an applied problem, a specific solution, and a general formalism. That would be the nice way for things to go. I'm going to try and present 3 papers to you that are at different points in this chain. So the first paper I'm going to present is an applied problem for which there's a specific solution. But when you look at it, hopefully you will see that it's begging out for something more general. Then I will show you what that general formalism can look like in one project where we've actually tried to make something from a specific solution with general formalism. And finally, I'll show you a paper that's me throwing up my hands, a very clear applied problem where even the specific solution itself is kind of missing, but where we need it. And so the goal of this talk is not so much to show you stuff I've done. It's instead, I remember as a grad student and as a junior faculty member, the hardest thing that I found was figuring out where to work. And so I'm hopeful by showing you this, you'll have some sense of work with lots of holes, and that these are areas that I think are extremely rich areas in which minds like yours are needed. So let me dive in. So these are the 3 projects. I'll start with project 1. Project 1 starts in a very unsavory place. So in the United States, there are about 12 million arrests, which is an extremely large number. For a country of 300 million people, it's an impressive number, let's just say. And right after arrest, a judge has to make a decision. The decision has nothing to do with guilt or innocence. The decision merely has to do with where should you wait for trial? Wait at home, or should you wait it in this place? This is one of the more consequential decisions that can be made for you. It's made in about 5 minutes. It's consequential because if the judge says, oh, you should wait in jail, the average jail stay is about 2 to 3 months. In some cases, as high as 9 to 12 months. 2 to 3 months, that's pretty much the end of your life as you know it. You've lost your job, things are pretty bad. What is the judge doing when they make that decision? Well, their job by law is simply to predict the risk of the defendant on whether they'll commit a crime when they're released and whether they're a flight risk. So a while back, more than 5 years ago, maybe 8 years ago, if you look at this and you look at the judge's task, see the individual, look at their background, and predict jail risk. Predict flight risk. This is a perfect supervised learning. In fact, you could say the judge is a supervised learner. So you could actually ask the question whether judges are doing a good job. That's a behavioral question answered using a machine learning technique, because what would you do? You would form a statistical predictor of flight risk or jailing risk, flight risk or crime risk, and you would assess the judge against that benchmark. So in that paper, we asked the question, can algorithms improve judicial decision making? And I'm going to abstract from a bunch of stuff that I'll tell you in a second, but the gist of that paper is that judges really make big mistakes. So to calibrate the size of the mistake, you could keep the crime rate fixed and reduce jail populations by 40%. That's about the magnitude of the error judges are making. But alternatively, keep jail populations fixed and reduce crime rate by 4%. Getting to these numbers, there's a lot of subtle but super first-order issues. I'm not glossing over them because I don't think they're important. That was the entire point of that paper. That was the point of a much more carefully done paper. If this paper was the hack, there's a recent paper by Ashish Rambachan, which is a much more formal thing, which basically just says it's actually very hard to compare human decision makers to statistical predictors because you don't have all the labels available. You don't know the outcomes for the people who went to jail. You don't know the payoff, the exact payoff the person is optimizing. There's a lot to be done. But top line, take this as given and assume the point of this paper. What bothered us for some time after writing this paper is a different question, which is, okay, let's assume this result is true. Why can algorithms improve judicial decision making? What's the judge getting wrong? Yeah.
Treated the same? Like,
that's all the stuff that goes into this. That's exactly.
No, level in crime, so some crime is more.
Oh, absolutely. Some crime is worth a lot more than this. Yeah.
In the study, is it considered? Or?
Oh, that is what goes under omitted payoff bias. Yes. because the payoffs are different across it. Everything you can think of, this is the downside and upside of economics. You write 100-page papers, you deal with all that stuff. That stuff you thought of, and we can go through it, but let's, yeah. Okay, so why can algorithms improve judicial decision making? How would we go about answering that question? What's funny about how we'd answer that question is very straightforward, at least in most disciplines. Well, we come up with a hypothesis, and then we test it. So if our graphic were to show you this elaborate procedure, it's hypothesis to testing. And when it came to testing, there is a collective understanding of an endless number of ways of testing things. We have lab experiments, field experiments, structural estimators, observational causal inference. We have like a ton of material to do this once I have the hypothesis. But what about that bit? Where does the hypothesis itself come from? Well, it's kind of funny. It's just I thought of it, just human intuition. There's a remarkable asymmetry here between the meticulousness of this bit and the haphazardness of this bit. So it's not just asymmetric, it's a little hypocritical. If the original paper is saying judges make behavioral mistakes because it's hard for them to process all this data and see all the correlations correctly, well, what are we as scientists but people trying to come up with ideas based on what we see generating hypotheses? If the judge isn't great or perfect at looking at stuff, well, maybe we aren't either. So why can't, if the supervised learning algorithm can help the judge see things in data that they might not be able to see, why can't it help us see things that we might not be able to see? It would be kind of weird if as scientists we were immune to the same thing as the objects we were studying. So how would we do that practically? So let's go back to the original paper. In the original paper, we had an algorithm trained to look at the defendant's outcomes and predict defendant risk, and compared it to the judge looking at the defendant and predicting defendant risk. But let's turn the camera around from the defendant back towards the judge. Now let's predict the judge's decision. So now we have an algorithmic model of the judge. So somewhere in that model could be an insight that might lead to a hypothesis. But we have to kind of pull it out. So let me try to pull it out first, incredibly crudely. I am not supportive of what I'm about to do whatsoever. It's just a way to get going. It's a terrible thing to do. Don't do it. What we do is we take that big COMNET that just predicted the judge, and we just do variable importance. We take variables, we shuffle them, and we ask, which variable, were we to destroy its information content, would we lose the most predictive quality on the judge for the fixed predictor, okay? That's got a lot of problems. We can talk about it, but it kind of gets us thinking. When we do that, the fifth most important factor, by which I mean, were we to lose information about this, our prediction quality of the judge would drop a lot, is whether the current charge is a drug crime. Fourth most important factor is whether the current charge is a felony crime. Third most important factor is property crime. Well, you can see where this is going. Second most important, violent crime. So you can see that from this, these are the top 5 factors. Anyone want to guess what current charge is missing? Kind of see the ones that are up here. Homicide. That's pretty, right? You can imagine it's more violent than violent crime. Yeah. In fact, oh, yeah. So that's much closer than homicide. Yeah. It's the, oh, yeah. Age, that does it. Yeah. That's a very good guess. Turns out that it's the current charge of having the wrong face. That is, the mugshot is the single most important factor in the predictive model of the judge. That's actually a lie. It's one of those lies you tell in statistics by like scaling things. Because when I do it this way, it sounds like, oh, the mugshot matters, so do these. Here's a different way to see why how much the mugshot matters. We simply, and I should say this is just the pixels. This isn't some features we created from the mugshot. Here's a different way to say it. Suppose I formed a new predictor, and that predictive algorithm only has the mugshot. And from the mugshot, it is asked simply to predict, will this person be jailed or released? So none of the other information. Turns out the new predictor explains about half of the entire predictable variation in what the judge will do. That's the sense in which this ranking is a lie. About half of the predictable R-squared is sitting here, and the rest is down, way down here, this small distribution of accumulated stuff. So the mugshot plays an insanely large role in what the judge does. But as you two said, in some sense, the first step in understanding if there's something here, if there's a hypothesis, is that that magnitude is a surprise to me. But we already have hypotheses as to why the mugshot should matter, right? We had age, we had race, gender. So the first thing we have to do is check if there's new signal in the face. So, race, skin color, age. I didn't put gender here. Gender is the most important factor, actually, of these. I don't know, I just left it up. After that, I think goes age, then skin color. Skin color matters a lot more than race. In fact, conditional on skin color, race goes in and out of the equation. Skin color is like extremely important. So you have to check that those matter. But that's a weird place to stop. Psychologists have been studying faces for a long time, so they have a bunch of hypotheses about which feature of the face matters. That would also be a weird place to stop, because if you give a seminar, part of the problem is everyone is free to invent up their own random thing. Are you sure it isn't whether there's a tattoo on the face? Are you sure it's like people can come up with their own hypotheses? So the third thing you have to do, which we did, is we had people look at these faces and play an incentivized game where they tried their best to guess, will this person be jailed or released? So now we've got factors identified by science, demographics, things identified by social science, and then human predictions. We've done this game with public defenders who are like knowledgeable about this area. You can do however you want. But what's striking to me is that if you condition on these things and ask, do they matter? Is the algorithm still matter? So the first fact is that all of these are rediscovered by this algorithm. Conditional on the algorithm's prediction, none of these matter anymore, which is quite striking, because it's not like we went out and said, look for race, look for gender. I didn't code any of it. It just found these, even the personality features. But the other fact here is that collectively, they explain very little of what the algorithm has found. I think gender explains about 8% of the predictable variation. The rest together explain about 4%, 5%. So about 13% of what it's found is explained by what we would have known to look for. That includes the summary statistic of human predictions, which raises the question, what is inside of this ComNet that we hadn't considered? But of course, this is a classically hard problem because these algorithms are somewhat hard to interpret. So this is where I think the challenge of hypothesis generation begins. You have to bring yourself to the point where there's a black box predictive algorithm, and that black box predictive algorithm is got more signal than you can comprehend, but now you have a communication problem. And what you need is the algorithm, if I anthropomorphize, knows this M of X. What do we know? We have some non-formalizable set of interpretable facial features, which is actually a huge set if you think about it. Think of all the things you could name in it. It's a really big set. It's in the thousands for psychologists who study this. But what we need is a communication procedure where the two can talk, so to speak, and output some hypothesis from that set. How would we go about building this procedure? So here it would be the algorithm is discovered, but the human has named, is the way we would think about what is happening here. How would we go about building this? Well, a common interpretability approach uses gradient methods. And so gradient methods are pretty straightforward. So we have a ComNet that's predicting what the, that goes from faces, I'll just do it here. That goes from faces to predictions of whether the judge will jail the person. What is the face here, but sort of a matrix of red, green, and blue. It's a 3-channel matrix. So if we can zoom in, take one of these pixel values, say on red, we can differentiate and see how much the final prediction changes. We do that for all inputs of that face, and that gives us the gradient at that face, which input values would have largest effect on predictions. And so you would then isolate pixels that lead to big changes in predictive values, and then you would display that in a saliency map. Does that make sense to everybody? So basically, you would take the face, and I would show you where in the face would there be biggest effects of a change in value. Okay? So what we're really doing here is, this is, if we take image space and say this is every possible pixel combination, and we say there's a contour map of the prediction function. So take a specific face and form a gradient, and then just show that gradient to me on the face. That's all we're really doing. It's very straightforward, okay? So let's do that. Let's start with this face. Then let's like apply the procedure, and it turns out you get this saliency map. And you can do it for every face, and you get this. And what it remarkably tells you is that the algorithm is looking at the face. The remarkable discovery, but really not a useful one. Why doesn't it work for faces? It doesn't work for faces. If you've ever seen gradient methods, they're all about localization, about identifying where something might be happening. But facial features are not localized. Most of them are not. Tattoos would be it, but most things are not. There is no place in the face where trustworthiness sits. The worst part of giving this talk is that every time I reach this part in the talk, I'm just horribly convinced everyone's looking at my face. This is very awkward. But it's true that it's diffuse. And so localization doesn't really work there. Okay, fine. But you could say, you just haven't been smart enough. What you really need to do is you should just follow the gradient. And we've already done the gradient, so why don't we just go about and follow it, right? So I showed you that picture. Let me now change the photo and keep changing the photo so that I get a new photo, right? Rather than localizing to pixels. So great, let's do that. So people also comprehend through comparison, so let's change to increase in predicted value, literally follow the gradient. When you do that, you get this, which is, doesn't make any sense either. This is also a dismal failure. And what happened here? What happened here is a pretty general lesson, actually, that happens in every one of these black box predictors. It's extremely general. And you already should see it in this photo. So figure. This is the contour map, that's the gradient. So what I said was, well, why don't I just follow the gradient to a morphed face, right? But in this image, does anyone see their problem is already here, but I can't tell if it's one of those things like when you're teaching, you're like, I'm thinking of a number, what number is it? But anyone see this? Probably not. The problem is, this is image space. Most images are not faces. The prediction function is defined everywhere in input space, which is every pixel combination. But faces themselves are a tiny submanifold of all pixel combinations. It's 2 dimensions here. It's 1-dimensional here relative to 2 dimensions. But in fact, in reality, you could make pixel combinations for the rest of your life. All of us could, and we'll never stumble on a face. It's a much lower, it's orders of magnitude smaller. So if you started here and you moved, you will almost certainly move off the submanifold of faces and into somewhere in pixel space. That's why we saw this very weird, goofy thing. And generically, that's always a problem. Gradients may make sense locally, but they're nowhere respecting the actual structure of the input space. In this case, that the input is a face. It's not an image, it's a face. But this is fixable. To fix this, there's some, from earlier work we'd done, you just need to keep the original idea, but produce an independent model of the manifold and morph within the manifold. What is an independent model of the manifold? Well, that's an unsupervised learning task. That is exactly a task that says, model this subspace. And for faces, we actually have very good models of subspaces, or at least techniques for building these models. GANs work extremely well for faces. So what did we do? We then went and built a mugshot GAN. So we took all our mugshots, and now we can produce synthetic mugshots. In fact, all the mugshots I've shown you so far, they're not real people. They're all made up mugshots. They're all synthetic. I haven't shown you a real mugshot yet. Here is the first time I'll show you that 2 of these people are real mugshots and 2 of these are fake. But I never remember which. I think it's the bottom 2 that are real. I don't know. Some pair are real. And so now our communication procedure is going to be to take that mugshot, take the judge predictor, take the GAN, morph, stay within the manifold space, produce, this is an example, I start with somebody, I make it much lower detention probability here, much higher detention probability there. I form image pairs, left and right. I show those pairs to people in a game that's not us, and they're asked to guess which is higher predicted release. They're given feedback so they have a chance to learn. They're given incentives, and at the end, I'm going to ask them, so what do you think the algorithm was looking at now that you've learned to sort of. Subjects kind of learn to do pretty well at this game, which means that pretty well. They learn to communicate with reliability, that they're able to guess which one is the one the algorithm is going to predicted release. There's no real labels here. This is truly just communicating with the predictor. And once they've done that, we get their words. And so what do they say? Well, here's a word cloud, and you can start to see already kind of what's emerging here. So if you tokenize this and put it into space, what you find is about 40% of subjects say, oh, the well-groomed person is the one who's going to be released. So it turns out if you have somebody else code the mugshots for well-groomed, in fact, well-groomed does an extremely good job of predicting whether a person, in the real data, whether a person will be released or not. The well-groomed effect is much bigger than the race effect. It's about 1/2 the effect of having murdered somebody. So a good argument to shave, I guess. But of course, there's more where this comes from. Well-groomed only explains, I think, about 10% of the predictable variation. Yeah.
One of the features that had been known that you had tested before?
No. Yeah, it's not a thing that showed up when you ask public defenders.
No, I mean, psychologists.
Oh yeah, no, yeah. But of course, there's more where this came from because we just had comparisons, and all we did was show those comparisons to people. We can just keep going. We can just orthogonalize against well-groomed and keep morphing. So there's a technical challenge here, which I can honestly tell you, we absolutely did not solve it any way other than with duct tape. Maybe this whole thing looks like it's with duct tape, fine. Then the technical challenge we solved here is with gum, basically. It's a very deep challenge. Because when I said I'm just going to orthogonalize, it seems like, sure, you will. Okay, but think about it. In GAN space, I don't have well-groomed. In GAN space, I can only have a predictor of well-groomed. So I'm only going to orthogonalize against predicted well-groomed. Okay, but predicted well-groomed is imperfect. So as I orthogonalize and keep moving, the accumulated error of that thing will almost always be such that you're still moving in well-groomed space because that was the first order signal. In other words, the procedure picks up on the misprediction of the thing that you're orthogonalizing against and continues to keep well-groomed in the face. So we can talk about how we did it. There is gum here, but it works, but I certainly wouldn't think that I've got any deep insight into why it works. But that's the conceptual problem. There's another weird puzzle here, which is we did it two ways. I'll show it to you for this inner orthogonalization process. When you do this, you then do get some pictures out, and you get a second thing. The second thing is actually seen by these photos, actually very cleanly. And subjects, this one is much easier to see. Well-groomed, you kind of but this one people quickly see, and it's easier for subjects to see this in the second go around. And it's in fact, people say full-faced, heavy-faced, fat-faced. Actually, by show of hands, how many people think full-faced people are more likely to be released? People that think they're more likely to be jailed. But it usually goes half-half. In fact, full-faced people are much more likely to be released. A second oddity with full-faced is that it's actually got a much more signal for the original predictor than well-groomed. Well-groomed is not the highest value signal, which is also kind of interesting because we just followed the gradient. I suspect what's happening is built into the GAN, some features are just better represented in the GAN. Facial hair, I think, is just extremely overrepresented in the GAN. I think that's why we find it first. I actually think if we were to do this a third time, we might find a feature that's even bigger than well-groomed. I think the GAN gives you a bias in what you can discover. It's not a neutral representation of the distribution. what I think is happening here. Anyway, so you find these two. I'm going to stop the story here because this is sort of a proof of concept. You have full-faced and you have well-groomed, you can go back and ask, do these actually predict judge behavior? Back to the real data, code up photos, and you find, yes, they do. Like well-groomed people are much more likely to be released, big magnitudes, as I said, and heavy-faced people are also much less likely to be released. Again, big magnitudes. Think of it as 40 to 50% of the magnitude of the violent crime rate is what you're finding here. Are these new? I mentioned they're experimenters with public defenders. I did not want to do this, but it's very hard to write a paper on hypothesis generation without somebody telling you also need to test the hypothesis, which seems like a goofy activity because it's a paper on hypothesis generation, but no matter how often you point at the word generation, they want to say you should test it. So we did some lab experiments where you actually can just give subjects like the description, the rap sheet, everything, and say, do you think this person should be jailed? Do you think this person will be jailed? Whatever you want. And then you can experimentally manipulate the actual face so that it's more well-groomed or more full-faced. And you actually see subjects behaving a lot like judges do in the correlational data. So for whatever that's worth. But this is not a paper about well-groomed or full-faced, though if you want to take life lessons from it, so be it. It's not a paper about judges. It's really a paper about a way to study people and a new way to generate hypotheses. And I hope you see not just from images, but from really any high-dimensional input. And what I was hoping to get you to see is that this is a problem where we started with a very specific applied problem. We've got a relatively specific solution, but there are a bunch of questions that sit on this frontier. Questions that there's just nowhere I would even know to turn to in the literature. For example, how would you think about the quality of a hypothesis generation engine? How would you measure it? You all know how to measure whether a hypothesis is correct. You know how to measure a predictive algorithm's accuracy. But what is even the criteria you would use to do this? I have no idea. I don't even know what I would write down. If your eventual interest is causal, should you even be looking at all correlations? Because that's all this thing is doing. It's just a black box predictive model. I don't know. I have no idea. Is morphing itself a hack, or is there some general insight here that morphing belies that is the way to generate hypotheses and communicate with people? Finally, I'll end on this one, which is that I think the interpretability literature in machine learning has stumbled often because it was not as obvious what the end use case would be for the interpretation. Well, here we have a very clear end use case, very specific. Not quite formalizable, but eventually probably formalizable, which then raises the question, if you knew that, could you really start to think more seriously about what, quote, interpretability means, at least in this context? So you can see in this paper, for me, I'm interested working at this level. This is like the crop level. But a bunch of issues have unearthed, including issues that, if I was being honest with you, I'm not even quite sure what a hypothesis is. Like, you don't really need to know what a hypothesis is, and you'll see that in the next paper. Because for you, everything starts once you instantiate the hypothesis in the statistical model of the data you have. But the hypothesis sits outside of your formal model. You never need to think about it. Okay, so that's the first paper. Let me walk through the second paper. This is one that tries to, it doesn't close the loop, but tries to go to the other side. Yeah. Yeah.
Does the judge know about your profession or employment when making the decision?
Yeah. All right, so let's try on this one. So this one, it's related to the previous one, but it says, oh, since we had all that, why don't we think a little bit about machine learning for science? Now, for those of you who have been following this area, I'd say probably protein folding is a good canonical use case. AlphaFold success is a good example. You can kind of see this here. But there are many such examples. AlphaFold is not the only example, but what they tend to do is you tend to take a theory that's kind of hard to compute. hard to compute understates it. Yes, you have a theory, but it is literally impossible to just brute force your way through it. And the ML pipeline is actually making this theory tractable for us. That's really what's happening in the protein folding world. It's also what's happening in most of these things, like discovering faster matrix multiplication, autonomous discovery of battery electrolytes. Material science is a very popular area for this because, again, quantum mechanics is well understood, but it's also not computable up to the level of materials. So it's sort of taking hard to compute micro theories and making them tractable. This all works. This part of ML for science works because it is in a world where the theories are really good. Quantum mechanics is a good theory. Unfortunately, that's not the world I work in. Our theories of people are, let's just say, slightly less good. Maybe we can call them incomplete, incorrect. And our problems there are not about trying to make those theories tractable. Our problems are, man, those theories need help, and they're about making them better. The different kind of use for ML for science, and I just want to think a little bit about that. You could view the previous paper through this lens and say, when the theory we have is imperfect, can we generate hypotheses against it? That's when the theory is implicit. In our heads, we have some notions, but it's not a formal theory. But there are many places in social science and behavioral sciences where we have an explicit theory, where we actually model things, and then we try to make those models better. What actually happens, how do people improve theories currently in those cases? When you go back and look at it, let's look at theories of choice under uncertainty. So the discovery of expected utility theory was like extremely important for many, many disciplines. You sort of axiomatize how people choose between lotteries, you get these expected utility theories. The first big sort of, I'd say, attempt to make expected utility theory better came from something called the LA paradox. How many of you know what the LA paradox is? Maurice Allais was a mathematician, maybe economist, and he basically said, oh, this theory is really, the axioms are great, it all looks really good. I just want to show you something. What I want to show you is, imagine two lotteries. Lottery A, you can win $1 million. Lottery B, you have an 89% chance of winning $1 million, 10% chance of winning $5 million, but 1% chance of losing everything. Most people are like, I don't want to mess with this. I'm going with lottery A, right? I assume if I made the numbers big enough, you all seem very wealthy, so add another 0 there, 10 million or something. Okay. And then LA was like, good, we all agree, most people would choose A. I'm gonna show you another menu now. In the other menu, lottery C, 89% chance you get nothing. 11% chance you get $1 million. Or lottery D, 90% chance you get nothing. Or 11, it's like, which one? Everyone's like, D, why is this even a choice? This is so dumb. Then LA said, yeah, that makes sense. That's what I would do too. Unfortunately, these two choices are completely inconsistent with expected utility theory. They violate the axiom of independence. These are just, you can add a lottery to this, you can add a lottery to this one to reproduce this one. The other way around, you can have this right. Yeah, you can add lotteries to these to get from one to the other. You can see why that is once you see them side by side. The amazing thing about the LA paradox was you don't even need to collect data on it. You've just seen it. You're now like, oh man, something is wrong with expected utility theory. The other amazing thing about the LA paradox is I don't even know what this thing is. Like, is it a hypothesis test? No, LA didn't collect thousands of lotteries and do a t-test. It's a little weird. You'd say, well, that's an odd one-off situation. Actually, no. Then came the common ratio effect. Then came the anomalies by Kahneman and Tversky. Those anomalies, when people looked at them, they said, oh, I think we see what's wrong. It's all in the independence axiom. We're going to fix it. And that led to prospect theory, which was sort of Kahneman and Tversky's major contribution. Of course, from prospect theory, once you had that theory in hand, people are like, I've been looking at this thing, and I've got some more anomalies. And that led to new theories, and this process is kind of developing. In fact, this is not unusual. Nearly every field tends to develop by objects like the LA paradox. So in game theory, the first theory was Nash. Then Reinhard Zelton said, I'm going to show you something called the chain supermarket paradox. He's like, isn't it weird? The Nash equilibrium there just looks goofy. It does look goofy. That's why now we're going to do subgame perfection. Then somebody else says, oh, just look at this game. Doesn't the weird behavior look weird? So, oh, it does look weird. That's why we have Bayesian subgame perfect, and so on until we kind of went forward and forward. That's what happened in finance with CAP-M, consumption CAP-M. You can go through every field you want, not just in social science. Early physical sciences, before they settled down to extremely good theories, were often like this. Many people think of Galileo's experiment on the Tower of Pisa as exactly this. You architect this perfect thing, 2 balls that were exactly the same shape, exactly the same size. One was hollowed out, so the mass was different. And then you say, let's drop them. You think this one's going to fall faster. Let's see what happens. Oh no, they fall at the same time. What's going on? So in many ways, these anomalies are what are used to improve theories. How do we usually find anomalies? Well, the way we usually find anomalies is there's a person. They look at the world. They contrast it with the theory. They're usually very creative and very smart, and they say, I've got an anomaly for you. Think of the genius of LA to just like find that exact pair of things to show you what was wrong. Okay. This is done by people, that's done by people, that's done by people. So the question in this paper, much like the Faces paper, is why does this need to be done by people? Like, take this bit. As in the Faces paper, I don't know, algorithms can look at the world and see lots of signals. But they can get a lot of predictive signal here. Maybe we can just automate this entire pipeline. And maybe we can create a box, an algorithmic box, that can make a procedure call to a local predictive box here, but is an algorithm that does that, takes as an input a theory, and then crafts its own anomalies. And could we do that? That's what we're doing in this. This is a paper with Ashish Rambachan. So it's just an algorithm that takes a data set, a theory, and crafts anomalies for that theory that are implied by that data set. To be clear, I don't mean find subset of rows. I don't mean any of that. I just mean the predictive model implied by that data set. What would be a new set of instances? These are never in the data set. These are crafted by the algorithm. So the automatic anomaly generation problem is basically this: theory, predictor, anomalies. You don't even need the data set. You just need the predictor, basically. It turns out that in the process of doing this, there's several hard things. The first hard thing is I actually don't know what a theory is. Kind of odd. You may say that's because you're an idiot. That's a plausible hypothesis. But then again, you don't know what a hypothesis is. So there you go. I don't mean any one theory. Of course, every theory we have, almost every theory we have, is formalized. But I mean, what is the mathematical collection of theories? You'll notice we face a weird diversity problem here. That's because every theory we have is often in very different representations from each other. Some theories are axiomatic. Some theories, like CAP-M, is just an equation. Some theories are function classes. Across the theories we possess, they don't all share any sort of mathematical framework. So the first bit that's hard here is literally putting all these theories into a common framework. The second thing that's hard here is it's unclear what an anomaly is. I can point to LA, I can point to subgame perfect, but you kind of have to define what that is. And again, that's kind of odd. And an anomaly is not misspecifying model, tests for any specific, it doesn't even have data. It's an abstract object. Here, look at these instances I've created. And notice how different they are from everything you know. And what we need is a framework that simultaneously encompasses statistical objects like machine learning, data generating processes, with logical objects, because a theory is just a logical object. A theory does not actually sit adjacent to any data. You make it adjacent to data, but it sits being able to talk in the world of theory. You can derive things, you can make logical consequences. Okay, so I'm gonna, in the interest of time, I'm gonna skip those bits. But once you have those bits, you can then develop a procedure for generating anomalies. And that procedure turns out to be kind of interesting. So it turns out to be an equilibrium in a game. The game is the following. The falsifier, who's trying to create an anomaly, proposes a data set, like LA is a data set of size 2. It's menu 1, menu 2. Here are 2 menus. Given the data set, and given the algorithmic prediction on the data set, the theory says, oh, I can explain that behavior in this way. So the theory is trying to minimize the loss, and the theory explains, the theory is trying to minimize the loss, find its explanations that it can use to explain away whatever has been found, and the falsifier is trying to maximize the loss. So it's actually a max-min game. And anomaly generation is just max-min optimization of finding the smallest proposal data set that the falsifier can propose, that the theory can say, oh, I don't really have an explanation for that. I guess I'm screwed. That's what LA is. LA has found a point in that space. Isn't it funny that this actually is very, very analogous to data poisoning attacks? Because that's what data poisoning attacks are doing. And that's why you end up with the same max-min structure. So for those of you who don't know data poisoning attacks are exactly the type where you have an algorithm that's a panda, a classifier, a visual classifier here that says this is a panda, this is a pig. And the data poisoning attack says, I'm going to add something as small as I possibly can so that it still looks like a panda to you or a pig to you, but the classifier is now fooled. That's also got the same max-min structure. And so you can actually use that same max-min structure. There's been recent breakthroughs in these non-convex, non-concave optimization problems to do this, and you actually can then generate an anomaly detector. So the anomaly detector basically takes any theory and any predictive model and does it. So does it actually work? So we'll go back to expected utility theory and apply it to lottery choices there. Let me show you what we do. We start here and ask, let's put ourselves back at this point in time. And let's play forward history, but without these people and just the algorithm. And what you tend to find is, in fact, it generates a ton of anomalies just from the raw data. And these anomalies are all the known anomalies fit into these 2 bins. In fact, known anomalies to this date fit into these 2 bins. And weirdly, it generates a ton more new anomalies. And the vast majority of the anomalies it generates are nowhere in the literature. And they're actually simpler. Some of them are much simpler than anything that's been in the literature. But of course, these are just proposed anomalies. That doesn't mean these are actually true. So what we could do is we now take these, because these anomalies are no harder than LA. They're just like, give people this menu of 2 lotteries, give other people this menu of 2 lotteries, see what you find. So when you do that, you can actually get an estimate of the population level rate of inconsistency with the theory. So these are the numbers for each column here is a different anomaly, and the height is the height of the population level inconsistency. It's hard to know what to make with this table. So we need a benchmark, and the benchmark is, you know where the LA paradox falls if you run it on people. There's another very common one called the certainty effect, and there's another one called the common ratio effect. So it's actually quite striking. It's not that these are by no means the strongest anomalies, though some of them are stronger than the strongest human-found anomaly. But as a collective, they're all at about the same magnitude of population violation as the anomalies. And so this paper, I think, falls into the specific solution general formalism, but which then opens up a bunch of questions about this general formalism that I just feel like I have no idea. So one question I have is, when you look at these anomalies and start thinking of them as real objects, there's a question of how dense are anomalies in the space of examples. They're not that dense. They're actually quite rare. And do we care if anomalies are rare? If you look at historically discovered anomalies, we've never said, hey, that's a very rare event. 2 balls of the exact same shape falling off a tower. I guess we really shouldn't care. But that already tells you something. Theory seems to fixate on extremely rare events. Theory development fixates on very rare events, whereas we often tend to fixate on some population averages. So it's unclear why there's a mismatch between how theories think and how statistics think. Here's another one. How do we make these anomalies more interpretable? It's just outputting these objects is finding the smallest objects, and I just don't even know. Like in our case, because with lotteries, they were all pretty interpretable. I'm pretty sure if we turn this loose on other things, we're going to encounter some anomalies that we look at and go, what the hell is that? And in our work, we presume the smallest anomaly is the most informative anomaly. It's kind of a weird Occam's razor turned around type situation. And certainly historically, when you look at the history of science, people have often produced the smallest anomalies they can to try to chip everything away. I have no idea why that should be true, or if it's true. And so let me stop there. That's the whole, and you can see in both of these projects, in this one, sure, we got to this point, but it kind of opens more questions than it kind of answered. So let me use the last few minutes to just tell you very quickly about an applied problem where I just stop right here. Okay. So here's the applied problem. It's very easy. It's about Facebook. I guess many of you probably don't know what Facebook is because you're so young. It's like a TikTok for photos. We had basically, in a nutshell, subjects were scrolling through Facebook while screen sharing. All we did is we recorded how much they liked each post. They told us, did you like that post? How much you like it? And we also recorded other features of the post. Okay? So I'm going to show you what we found. On the x-axis, we took everyone did 60 posts for us. We have their self-reported preference. On the y-axis, we have where the post was ranked. I have some great news for Meta. Their recommender system works. Wow, it's exciting. People's self-reported preferences correlate with where they're ranked. Liked more, higher ranked. Then something weird happens. We also recorded the race of the person who was posting. These are people's friends. And what we found was that conditional on how much you like it, so conditional on the x-axis, the Facebook newsfeed algorithm demotes posts by people who are not of your demographic group, conditional on how much you like it. This is not saying people don't want to see those posts. Maybe they don't. That would be on the x-axis. That would be on the distribution on the x-axis. This is saying based on how much they actually report wanting to see that post. You see a big gap. There are many ways to interpret this, so let's keep going for a bit. But outgroup posts are ranked lower conditional on preference. That's what I want you to take away. Second thing, we audited a second algorithm called People You May Know. Very similar. Ranks people for you. We do the exact same activity. In this case, how much do you want to be friends with this person? How much did you want to be shown this thing? Y-axis, where were they ranked? As before, we see a relationship, but now there is absolutely no in-group bias by the algorithm. It's also a little weird. It's not that you couldn't explain this pattern. You can explain any pattern. It's just 2 data points. But I think if I'd gone in, I would have expected making friends. There's much more room for weird shit to creep in than in clicking on posts of friends you've already chosen to make. So what's happening here? Well, we redid the audits in India with Muslims and Hindus, and you see exactly the same pattern. In fact, we've done this about 4 or 5 times now, but you see the exact same pattern. So why is there this difference? Well, without working with Facebook, I'm never going to be able to explicitly answer this question exactly. Even with working with Facebook, it's not immediately obvious because these are just 2 such different contexts. There's too many things different between these contexts. But I'm going to give you a hypothesis, and I'll stop it, and I'll give you a little bit of evidence, and then I'll stop. So what's my hypothesis? My hypothesis related to something happened to me a while back. I went to a friend's house. She was a very nice friend. It was like 2:30 in the afternoon. We were supposed to hang out. And it wasn't lunchtime, it wasn't dinner time. It was that time in between. She's like, oh, well, I'll put out some snacks because I'm a hospitable person. So she put out some Doritos. And I like Doritos. So I ate them all. She's very hospitable. So she put out more Doritos. And I really like Doritos. And she's very hospitable. And I really like Doritos. And you see where this is going. I ate a lot of Doritos that afternoon. And she was very nice. And as I was walking out there, I was thinking, wow, what a nice person. I am definitely never going back there again. So what went wrong? Well, first of all, it's clear. I went wrong. I have a problem with Doritos, and I'm not trying to, take the blame off of myself. That's clear. But I want to also argue she did something very wrong. What did she do? She was trying to do the right thing. She wanted to give me what I wanted, right? But did she give me what I want? Well, obviously not. What did she actually do? She gave me what I ate. Any behavioral scientist will tell you What people eat does not equal what they want, and our choices do not equal our preferences. There are many things we do in behavior and many things we choose that are not the things we actually want. This is probably the most basic insight of any behavioral economics, behavioral science psychology, is that choices don't equal preferences. Well, choices not equal to preferences would, in Facebook, play out very well here. Because guess what? My clicks definitely don't equal my preferences. And how is newsfeed trained? It's not even clicks, it's hover time. Does my hover time reflect my preferences? Not obvious. So that would explain this. But why? How would this explain the newsfeed versus people you may know? Well, I don't know. Hey, you probably, this is my favorite cartoon. This is my favorite cartoon of all time. It's got two different psychological insights in it, which is quite hard to pack into a cartoon. But in-group bias, our favoritism, is well documented. But it is a thing that is, we have favor more own group more in behavior than in preference. That's the key. It's that I behave more in one way than I actually want. It's a kind of bias above and beyond what I want to be doing. But it has another structure. Because it's the wedge between behavior and choice, behavior and preference, that wedge tends to grow when we behave automatically. For example, when you're not thinking much and it's not worth much to you, when you act quickly, when the consequences are low, those are all the times when in-group bias is largest. In which of these two do you think you act the most automatically? Pretty clear. These are the situations where there's less thoughtful, and that's where we're finding automaticity. This is a situation where there's more favoritism. Of course, this is all ex post. How would we test this? I will just quickly tell you, we did a lab experiment where everything is controlled, where we manipulate automaticity. And when you manipulate automaticity, I'll skip the experiment, I'll show you the results because I can stop there. Manipulate automaticity, what you find is people who are acting automatically experimentally, algorithms trained on their behavior show very little bias. Algorithms trained on people behaving more automatically, exact same context, it's just an experimental manipulation, suddenly algorithmic bias shows up. I'm not saying this is people you might know newsfeed, but that is what's happening here. So what I want to end on is just by saying, this paper has made me aware of something. The ML approach predicts easy to measure behavior and uses those predictions to drive decisions, whatever the decisions are. Implicit in those decisions is some presumption about human behavior, such that the behavior in the data matches preferences. And that problem transcends social media. It's in recommender system, but it's also in hiring algorithms. It's also in pricing algorithms. It's everywhere because we take behavior to be quite revealing of whatever the person wanted to do. The challenge I'll leave to you all is, I think there's something we could be doing called the inversion approach. For those of you who've ever done inversion, it shows up in many, many fields of physics. It shows up in medicine a lot. It's the following. The forward approach of modeling is, if I knew what's happening in the brain and I could see the biophysical level, I'd know what an EEG would pick up. But if all I have is the EEG, I have to invert back and guess what was happening in the brain. People who do inversion use the model of the forward to invert back. When you do that, it necessarily forces you to confront the uncertainty that there are many brain states that would have produced the same thing. My question to you is, how do we do this? How do we, in this context, incorporate formal models of human psychology into the prediction pipeline? For example, what would constitute a valid test of whether I built a recommender system that more closely adheres to what I actually want? And how would I incorporate these models? We've done it with EEGs. How would we do it here? And I'll skip this in the interest of time. These are the questions. And so let me conclude on this slide, which to me is the perfect illustration of arbitrage. And I think there's a lot of arbitrage to be done by people like you, because these questions are just sort of sitting there. There's kind of oranges being sold for $4, basically. All right, thank you.
A lot of Doritos for fun, and some orange juice to go with it, and buy it in Spanish. But there is a reception to follow, so please come and ask your great questions there, right in the back here. I'd love to have it. So,